Hello, my name is Ian Ozsvald, and I'll be talking today on Pandas 2 versus Polars versus Dask and versus one other library. Which data frame processing library should you be using in 2024? Apologies that I couldn't attend, huge apologies that I couldn't attend the Gaia conference. I was very much looking forward to being out there with you all. At the last minute, I had what appeared to be a family emergency, and I couldn't travel. Everything turned out to be fine. So please accept this video recording as a substitute, and I am open to answering questions if you want to send them over. So, who am I? My name is Ian Ozsvald. I'm an interim chief data scientist. So, I go into organizations and help the data science team become more valuable. Particularly, I add clarity to an often confused process. I'm really interested in making teams more highly performant. I've been in the field for 25 years. I'm a co author of O'Reilly's High Performance Python book. The second edition is out, and we're working on the third edition right now. And material from this talk comes from what we will be in that book later on. I'm a co-founder of the London-based PyData London meetup, which has grown over 10 years of volunteer efforts to 14,000 members with monthly meetups and an annual conference that raises £100,000 for the open source community. I'm hugely proud of everything that we've built there in that community. And along that strategic leadership line, I've ended up building a private data science leadership community called the Rebel AI Leadership Community, which is all about helping leaders make their teams more productive and more valuable, and just let people enjoy their jobs more. And my co-author, as we've developed this talk, is Giles Weaver. He wasn't coming out to present, a data scientist at a lot of prestigious organizations, also working on high performance issues and large data sets. So what are we talking on? Four interesting data frame libraries. I mentioned Pandas 2, which is turning into Pandas 3 this year. Polars, the data frame library that came out of nowhere and is hot on the heels of Pandas and is challenging it heavily. Dask, which lets us scale up our Pandas data frame manipulations and other Pythonic data science and numeric operations to multi-core, larger than RAM, and multi-machine operations. And also, I've added in a couple of slides on NVIDIA's new rapid CuDF Pandas accelerator. So accelerating Pandas to run on your GPU, which can offer some very impressive speedups under certain times. We've got benchmarks here, but remember, all benchmarks are lies, right? So these are based on my data set, my machine. Your situation will be different. Everyone's got benchmarks showing their library is best. Here we try to give a less biased view upon that, but your numbers, of course, will be different. What's the background for this talk? I needed a data set, and a year ago, with some buddies, not with Giles, but with some other buddies, we decided to do a charity car rally driving through Europe from London to Venice and back in a week, raising money for charity for Parkinson's, which was afflicting a member of family of one of my co-drivers. That was something silly. You had to go and drive a car over 20 years old, costing less than £1,000. We ended up driving an estate car, which was brilliant. There was another car we bought beforehand, which ideally you would want cars that don't explode. I'll mention that, and you'll have a picture on that a little bit later on in the talk. But this means, based on doing that charity car drive, we could go and pick up a large test file of data. So from the UK, from the Driving Vehicle Licensing Authority, we collected the MOT test data. So that's the vehicle roadworthiness test data, 17 years worth of vehicular data for whether vehicles, cars, trucks, motorbikes, and the like pass or fail their tests every year, and a whole bunch of other metadata. 30 million vehicles a year are tested and are on the roads in the UK, and the data is delivered as a mix of CSV, TSV files with different formats and different formatting errors, and clearly different export mechanisms that have been used to deliver them each year. So a bunch of processing is required, and we use Dask for that, and that made the job really easy, collating all of this different data into some Parquet data files for the base of our test. 600 million rows of data, comprising of date, time, integer, text, Boolean, which you can see some examples of at the bottom there. And the vehicle that we ended up, the first vehicle we bought, the one that blew up on us, the Volvo V50, you can see that on the government test site and represented in the data down at the bottom of the screen. So let's talk about these libraries. So Pandas 2, what's new in Pandas 2 and what prepares us for Pandas 3 later, hopefully in 2024? Well, Pandas, kind of 15 years old, originally based on NumPy with a column base, so a vector-based columnar access design, where it only had NumPy as a data storage backend. And then later in Pandas 1 going on 1.5, we saw the introduction of arrow-based data types, typically via PyArrow. And this gives us a different columnar storage engine, much more closely aligned with the storage that is used in Parquet files. And Parquet files have ended up taking over many large data estates that we might work with. So it reduces a point of friction for loading in data from Parquet, which is brilliant. But then it gives us two ways of storing data inside Pandas. Maybe there are trade-offs. There are trade-offs. Also, we see lots of internal cleanups, less RAM is being used, and it's paving the way for copy on write, a new mechanism which will be introduced in Pandas 3. And I've got some benchmarks where we turn it on and off. And you'll see that it offers some impressive speed and lower RAM requirements for Pandas 3. And you can enable this in Pandas 2, and you should be experimenting with it. You see on the right-hand side, I've got some of the logos. Pandas, Arrow, and NumPy use these logos throughout the slides to try to delimit different ways of doing some of the benchmarks. For example, on this slide here, so here we've got a grid. It's a 2x2 table with some screenshots from some of my timing code. Here on the top row, I'm using Apache Arrow, and on the bottom row, I'm using NumPy. You can see the icons on the left. And then the left column is about a string data type. So I'm using the %time_its timing mechanism to do repeated runs of an operation. And the operation is on the DFPDA, the data frame from Pandas, using Arrow as the backend. On the make column, so Toyota or Volkswagen, it's a string, so I can say .str.length, find out the length of that string. And with an arrow-based backend, that's the top left corner, 1 second for that operation on the 600 or so million rows of data, so pretty fast. Underneath it, bottom left corner, the same time it on DFPDN, that's the data frame Pandas with the NumPy backend, the make column str length, so the same API, different data backend, 8 seconds, so 8 times slower. That's pretty huge. And there's a note below it that NumPy strings are expensive, not just in operation speed, but also in terms of their RAM requirement. The 82 million rows that I used in this particular test, that was stored as nearly 40 gigabytes using the NumPy backend, or just 11 gigabytes, so a 4 times smaller data footprint using Arrow. So in this case with strings, Arrow is both faster and uses less RAM. So you might think, hey, Arrow is new, shiny, it's better than NumPy, we should always use it. On the right-hand side, top right, I show a group by in Arrow, DFPDA group by on cylinder capacity, taking the test mileage integer and performing a mean operation. That takes 2.5 seconds. Bottom right corner, I do the same operation, the same group by, same API on DFPDN, the NumPy equivalent, and it takes half the time, 1.2 seconds. Some operations are faster using Arrow, other operations are faster using NumPy. Probably all the Arrow slowdowns will be ameliorated over time and will end up at parity with NumPy, or in some cases, I'm pretty sure, faster. So it is the direction of travel, but just be aware it's not the simplest choice just to switch over to using Arrow right now. You do need to do a bit of benchmarking to check for your use case. I mentioned earlier on, copy on write is being introduced, and by default in Pandas 2, it's turned off, and you can turn it on. If you don't turn it off, if you don't turn it on, then you have the situation you see here. Some operations on a Pandas data frame force a copy to be made on every operation. So here, if I do dfpdn, so that's the NumPy backed Pandas data frame, I rename a column, that causes a copy to be made. I assign a new column, that causes a new copy of the entire data frame to be made with that additional column. And then I drop a column, but that causes another copy to be made. So you can see just underneath, highlighted in red, that 8.6 gigabytes of RAM were used in 17 seconds. And because these data frames are large and they're being copied, there's a temporary copy floating around. That copy costs about 9.6 gigabytes. And that little diagnostic comes from the tool that I've written, which is noted at the top of the screen, IPython memory usage. So you can pip install IPython memory usage, and then in your Jupyter notebooks, you get that diagnostic showing you how much RAM and CPU is being used during a cell's execution and the peak during the end-to-end part of that cell. And down below, I've got a couple of assert statements just to verify that I got exactly the output that I wanted. Because here I've turned on, I've enabled copy on write, and then I did the same rename, assign, drop operation. It used 70 megabytes in 3 seconds, and contrast that with 8.6 gigabytes in 17 seconds. So the only difference is I turned on copy on write. And with this new logic, Pandas says, oh, well, I want to rename a column. I don't need to copy the entire data frame. I just rename that column. I want to assign a new column. Well, I can make a view where this view looks upon the original data set, but the view has one extra column attached to it. I don't need to copy all of the other data. And I want to drop a column. Well, that new modified view, I can drop the necessary column and keep the rest of the columns as a view on the original underlying data and not do another copy. And below it, I've got the same assert statements, and you can see that nothing has changed there. There are some interesting little quirks in the overall memory performance. Some things are a little bit delayed, but overall, copy on write seems to just work, just go quicker, and just use less RAM. It's a very good idea to turn it on. You can turn it on with that pd.options.mode note that I've put at the top of the screen. And in Pandas 3, it's turned on by default. And some of your code may not work when it's turned on by default. There are a couple of dragons. You can read about those on the website. You should check that out. So what about Polars, this new data frame library that's come out of nowhere? Originally written as a Rust-based data frame library. It is Rust-based. That's the heart of Polars. But typically, data scientists don't use Rust. There will be some, of course, but typically they're not using Rust. So the author, Richie Vink, put a Python front end around it, and suddenly it became a competitor to Pandas, and then a lot of data scientists started to use it. So it's 3-4 years old. Only arrow based. So it's using the same memory model that Pandas has inside it, but that's first class and only class. There are no alternatives. There is no NumPy. It's inherently multicore and inherently parallelized. There's a query planner inside there with an eager and a lazy API. An eager API operates every single instruction as it's found. That's what we have in Pandas. A lazy API will concatenate a bunch of operations together and try to optimize them and then execute them when you ask it to do a computation. And it can even stream data from disk and an out-of-core, sort of larger than memory style, which I show here. So here's a slightly more advanced query. On the left, I've got the icons for Pandas and Arrow, and I'm using df-pda. And on the right, I've got the icons for Polars and Arrow, and I've got df-ple, df data frame, pl, Polars, eager, the eager mode. That was the base data frame. Then I've turned on the lazy query based planner to get some extra optimizations in there for a one-liner. So on the left-hand side, I drop a column, I do a group by, I ag, I query, I sort, a set of common operations, and using the arrow backend, that takes about 27 seconds. I can make it a little bit faster if I look at the note below. Pandas and NumPy does the same thing in 13 seconds, half the time, which is kind of cool. But look on the right-hand side, with Polars and the arrow backend, that same operation takes 3 seconds rather than approximately 30 seconds. So it's kind of 10 times faster, which is kind of amazing. That's the automated parallelization, trying to do some of the operations like the median and the count in parallel, and then trying to push operations through that stack of operations to find the optimal combination of execution. And just being a more modern data frame library, it can do some operations in a more efficient way than the older Pandas design. So some things are just generally faster in Polars, for a little syntax different, but generally just a very similar way of writing your code. It's really impressive. So maybe Pandas and Arrow is better than Pandas and NumPy. That depends on your data set, but generally it's not a bad idea. Polars seems to be faster than Pandas and Arrow, and Polars is using Arrow behind the scenes. Pandas copy on write seems to be a nice optimization, and we're going to have it by default in Pandas 3, so you should turn it on and try it on your own code base. I mentioned it's good to get a charity car that doesn't blow up. Within 24 hours of buying our first charity car, the Volvo V50 that was on that early slide, it tried to catch fire whilst I was driving it on a test drive in the UK. Totally not cool, and had to call the fire brigade to put the car out. Absolutely not what you want on the first day that you own a new car, which you're going to drive through Europe. So we had to find another car. And we'll get to that a bit later on. So what about doing another very common operation, resampling a time series? So here I've got here with polars, I've got a subset of the data from 2021 on to 2023, the data that was available when we wrote this version of the talk. And we're aggregating, so we're doing a resample, and then we're aggregating to count the number of vehicles that pass on initially a daily basis and then aggregated to a weekly basis. So you can see on the chart on the right-hand side, we're covering kind of 2 years worth of data. On a weekly basis, we get roughly 700,000 cars, kind of as a common maximum, being tested in the UK. So there are lots of these tests going on, but there's some strange dynamics there, right? If you look at that diagram on the right, there's a strange drop down, that green dotted line around April. And so I can ask the question, well, maybe that's a lockdown effect from COVID from a couple of years before. At Christmas, we expect a sharp decline because most of the test centers will close. But generally, during the course of a year, we'd expect a steady state testing environment rather than this huge dip followed by a recovery. So there's this hypothesis, if only we could put the data into RAM, but the data's too big to fit into RAM on my laptop. Isn't life a little bit difficult? Oh, well, not with polars. So with polars, I can just change that query from, on this slide, a read parquet, instantiating it all into memory in an eager fashion, to a scan parquet, by default lazy operation. I do exactly the same query. I collect, it takes 13 seconds. It's streaming in data from 850 partitions that are on the disk. That's the 640 million full data set. And then I get a multi-year view upon the data, and we can see that for 2018 and 2019, we had a roughly steady state, sort of 500,000 to 700,000 tests per week. And then April 2020, we had the lockdown for COVID in the UK, significant decline in the tests because all of the testing centers were closed, and then a gradual recovery over the years. And then this is kind of evening out, and we'd expect to see that continually evening out. So with polars, I want to switch from an in-memory data set. I don't want to have to batch and manage all of that. Turns out I can just scan my larger data set that's on disk, and it will do that batching behind the scenes for me and handle all of that. That's very impressive. What if we're curious about an even more complex query, looking at vehicle ownership? Can we see evidence of non-petrol and diesel internal combustion engines coming through in these MOT car tests? MOT car tests are delayed by 3 years. New vehicles don't have to be tested for 3 years. So we're not seeing the most recent 3 years worth of trend, but we can see this overall trend. Diesel in orange has been an increasing segment since 2006. Petrol has been roughly steady state, small changes, but roughly steady state. Overall vehicle ownership, unfortunately, continues to increase in the UK, and we see a little bit of green and a tiny bit of electric for hybrids and electric vehicles coming through in those MOT test data. And over the years, that will increase, of course. So that was a slightly more complicated query. And so here we get to play with Dask. So Dask lets us wrap up our Pandas data frames and lets us operate on data sets that are larger than RAM. So on the left-hand side, I've got a naive expression of my query to generate that previous graph. So it looks just like Pandas, and that's because Dask wraps up Pandas. Dask has a thin wrapper around a Pandas data frame. So every one of those Parquet partition files that we're reading in, that polars was reading in before, are read in through Dask and into Pandas. So we get basically the Pandas API, and most operations are expressed. But it's a manual interface. You have to know how to query it. For the one on the left, I'll talk about Dask expressions and the optimizations on the right in just a moment. So on the left-hand side, we do a Dask distributed data frame read parquet, reading in from a path which contains those hundreds of partition files. I do a query for vehicles that have passed. I do a little bit of cleanup on the fuel type, replacing a little bit of normalization. I assign a new year column based on a date manipulation. I do a group by. I do an aggregate. So I rename the aggregate, and then I do a compute because it's a lazy data frame. I have to tell it when to start computing. And then Dask goes off. It doesn't optimize very much. It just generally executes that sequence of instructions in a go. It takes 42 seconds. So it's pretty cool. It's very easy to get started with Dask, but it's not necessarily as fast as you might like. On the right-hand side, we have Dask expression. This is going to take over the main interface to Dask late 24 or maybe 2025. Here, we're getting a query optimizer added to Dask for the first time, so doing something similar to what Polars does. So we've got a new interface, the DX interface, the Dask expression interface, which is a set of replacement objects that wrap up the underlying Dask objects, but adds additional metadata, enabling query optimization. It's quite new. It was very new when we did the this version of the talk. It's improving every month. I would expect to see more operations coming in all the time. But you see, if you look at the code, it looks kind of the same. We couldn't do the query that wasn't supported in Dask expressions 2.4. It's been added since, but there are caveats around it. So we just got rid of it and did a DDF mask on test result comparing to P, the passed flag. The rest of the code is exactly the same. You call optimize. It does an optimization pass on the query that has been expressed on the DX object. And then you run it with a compute and it takes 26 seconds rather than 42. So that's a nice speed up for almost no work at all. On the left-hand side, we did our best possible optimization with Dask, and my colleague Jarves has done a lot of work with Dask, a lot of scaling work. He knows lots of tricks, pushing up some of the filtering, not to Dask, but into the read parquet, so it happens at the bytes on disk level, which is something that should be optimized for in Dask expressions at some point. Isn't yet, but should be in the future. And a few other optimizations. And on this query, we can squeak out a small improvement down to 23 seconds. On the right-hand side, we just wrote our polars. We didn't try to optimize it at all. We just wrote our polars with a scan parquet, so an implicit lazy data frame. Right at the end, we say, oh, streaming equals true and do a collect. Streaming equals true is a different way of streaming in a large data set. And then that collect, well, it just takes 24 seconds. It just worked. And interestingly, we required that streaming flag on Giles' smaller laptop with 32 gigabytes of RAM, or my larger 64 gigabyte of RAM laptop. I didn't have to use that streaming flag. I just left that off as the default. And in which case it loaded more into RAM. It used more of my RAM. It didn't run out of RAM, and the operation ran very quickly. So again, we see that Polars goes from just running the same query on an in-memory data set to running on a larger data set, even in a restricted RAM environment with a large data set. And it's just very fast without you having to do a lot of work, which is really quite impressive. And then final data frame library, CuDF. This is NVIDIA's CUDA for data frames library, which works on Pandas. It does not work at the moment on Polars. Inherently, it could, but it does not work on Polars at the moment. So it's a pretty new Pandas accelerator. It's been out for a couple of years. They made some new guarantees, 100% compatible at the end of 2023, and then they've been doing some big pushes. There are lots of big benchmarks out there showing how amazing it is. It is amazing. You do have to have a large GPU. I've got a 4 gigabyte GPU built into this laptop, and I can do some benchmarks, and I'll show those. And there are alternative interfaces. Here I'm showing the simplest interface, and it's this screenshot at the bottom. You do a load extension in your notebook for cudf.pandas, and as soon as you have enabled that, that's the first line on your notebook. As soon as you have enabled that, all of the subsequent pandas operations get rewritten to shuffle the data off to your GPU. So it copies it from main RAM into your GPU to execute it there. No changes are required. It should run faster, but it might run slower. It depends on how big your GPU is. Running out of VRAM is very easy, and that generates errors. So here's a very small demo, nice and easy. On the top, I've got the version running with Rapids, where I've enabled that extension on my laptop. I'm doing a time it on some fictitious data. I made this data set up as a little example. 10 million rows, 3 columns, about a gigabyte's worth of data, because I've only got a 4 gigabyte graphic card built into this machine. So this was my the first place where I started experimenting. I just write my pandas code, dataframe.group by A, ag on B, and then do some common aggregation operations. And when I run that with that %load extension, the load extension at the bottom there, enabling CuDF pandas, then that operation takes 40 milliseconds. The screenshot at the bottom, exactly the same line of code. I just commented out that load extension. So it runs in pandas on the CPU. That same operation on that 1 gigabyte of data takes 345 milliseconds, so kind of 10 times slower. So even with my built-in GPU, I can get a 10x speed up on a small data set for one line of code. That's really impressive. You do have to get CuDF and CUDA installed beforehand, and that takes a little bit of work. But once you've got it running on your environment, you do get this speed up. Separately, my Christmas treat to myself was to spend £1,000 buying an NVIDIA RTX 3090 card with 24 gigabytes of RAM. So sort of, I don't know, a third of the RAM that I have as my system RAM in my laptop. That's an external box in a Chroma enclosure. And when I run a larger data set, 400 million rows with that external graphic card attached, which is about 10 gigabytes worth of data, then relative to running it on the CPU, I get a 30 times speed up. So not a 10x, but a 30x speed up. So some of these operations can go really fast. It's really impressive. And I've been experimenting with CuDF a bit more. The error messages are a little bit obscure at times. It says, I can't support that, but actually maybe it does support it. Maybe you just run out of VRAM. There's a profiler that tells you how to use it, and there's an alternate interface where you can tell it which operations to send to the GPU, just for the ones that are bottlenecked, where the data would fit into the GPU, and you have much more control. So in a kind of a production scenario where you've got some tight bottlenecks for a lot of data to process, maybe it's a very interesting opportunity if you've got a large GPU. So let's get some conclusions. Polars is easy to use. You kind of should try it. It's a really nice library. It's inherently parallelized. It will use all of the cores and it will optimize your expressions without you having to do much work. You do have to learn the new syntax. It is a bit different. It's kind of PySpark-like syntax. If you know PySpark, the transition should be very, very lightweight. Pandas we all know, and Pandas keeps on getting faster too. More things run in parallel. You can use the number compiler in there, which you can't do in Polars. And you could use arrow data types. And you could use CuDF to export your data to the GPU to make it run faster there. So Pandas is still a very, very sensible choice, and currently still is the most popular choice. And you can use Dask to tackle larger data by just extending Pandas and just making it run on that larger data set, or multi-core on a single machine, 64 cores on a large desktop or server machine. You could use Dask to parallelize your Pandas in a couple of lines of code without having to change your code base. So that's definitely another interesting option for you. What happened with the rally? I know you're dying to know. We won it. So you didn't have to race with speed. You just had to do challenges every day. We won it. That was the Passat, our 24-year-old race-modified car that someone had had. We bought it secondhand. We put our surfboards on the top, turned it into a surf car. We won. We got some extra money. We put that into the charity, so more money for Parkinson's. And we're signed up for this year's rally, where this year we'll go to Venice and then on to Prague. Using the same vehicle, similar theme, raising money for Alzheimer's research, Alzheimer's Society in the UK. And we're going to go and buy a Bluetooth telematics unit so we can start getting sensor data out of the car. And then maybe there's an updated version of this talk, which has vehicle telemetry from a 24-year-old car as we cross the Alps. Maybe that's fun. So summary, we've got lots of options. You should go and play with these options. I'm super happy if you want to drop me an email and ask me a question based on your attendance at the Gaia conference. I've got a newsletter, notanumber.email. You can see all the past issues up there. I talk about the things that interest me. So I talk about the things like this for high performance work. I talk about the updates to my high performance Python book as we approach the 3rd edition. I talk about strategic data science leadership, that Rebel AI group that I mentioned. And I love receiving postcards. You can't see them, but on the wall behind me, I've got a set of postcards from past talks. I always ask at the end, send me a postcard if I've taught you something. People then send me an email. I give them my address. They send me a postcard. I stick it on the wall. It makes me happy. It's a physical reminder that these open source talks have value in the wider world. All right. Thank you very much for listening. I'm sorry again that I couldn't attend in person. I hope this has been interesting to you, and perhaps in the future we get to meet in person. Thank you very much.